Now, fill in the correct word or symbol the following statements. When a large number of samples of size n are taken from a population, then the distribution of the mean is known as the what, lads? It's the name of the exercise we're in. Huh? Okay, let's go back. I believe it's called the sampling distribution. Line, sampling, distribution of this mean. Okay, as the sample size increases, remember what we said yesterday. Imagine if I was taking, let's say, the percentage in your last maths test, and all of a sudden I pick two people at random. Somebody could be on at 85, and I could pick an 85 and a, for argument's sake, at 28. The standard deviation there would be huge. But if I take you in groups of 10, where there's a 28, let's say a 41, a 45, a couple of 50s, 60, 71, an 84, hell, I'll take you in groups of 8. All of a sudden you're noticing that the top score and the bottom score, they don't affect each other as much anymore. So therefore the standard deviation is lower, because all the results are more closely related to the mean. So what I'm trying to say is that as your sample size increases, this is n equals 2 and this is n equals 8. The more people you average, the more accurate your results are, and the lower your standard deviation becomes. The standard deviation will become lower or smaller. We cool with that? This carries over into, if the mean of the underlying population is mu, the mean of the sampling distribution of the means is also mu. Mean is unchanged. Okay? If the standard deviation from the population is sigma, and it's of size n are taken from it, then the standard deviation of the distribution of the sample means is, that's otherwise known as what? It's in your notes on page. It's sigma over root n. What's that called in your notes? Standard error. Isn't that correct? So it's sigma over root n, and it's known as a standard error. When you're talking about when you're talking about averaging means, you're talking standard error, not standard deviation. Standard error. Okay. Now, what happens when we average results? Does the standard deviation get better or worse when we average our results? Better. So the one with the smaller standard deviation is always the sampling distribution. So which one's the sampling distribution, do you reckon? What? A. Standard deviation gets smaller and mean or mode gets taller, and the means stay there, same. Okay? Does everybody understand why that happens? No. Alright, that's good. You're telling me you don't understand what that happens. That's fair enough, right? So imagine, for argument's sake, that I say that the weight of standard 18-year-olds is, for argument's sake, say 85 kilograms. Okay? Now, I'm talking about all the male 18-year-olds. Lads, I'm talking about all the male 18-year-olds in the country. And this is B. Okay? And this is diagram B. And what I'm saying is that the most common result for your weight will be 85 kilograms. The average amount is 85 kilograms. Hell, the median is 85 kilograms as well. Everybody cool with that? Now, so for argument's sake, if I pick a student at random, their most likely weight will be 85 kilograms, because that's the height, that's the top of the mountain, so to speak. Is that alright? Now, for argument's sake, standard deviation of 1.5 kilograms, is that okay with you guys? Something small. It'd be more than that. Sorry, 5 kilograms, right? Now, here's what I'm going to say. What I'm going to do is I'm going to go around all the schools in Ireland, alright? And I'm going to take samples of 10 students at a time. 10 students at a time. Is that okay? So I pick 10 of you at random. Now, my likelihood of picking one of you guys that is exactly 85 kilograms is reasonably low. However, when I average 10 of you, so for argument's sake, I'm just making up a couple of random numbers, okay, in order of size, alright? Probably went a bit too small there, to be honest. So here we go again. Okay, something like this. 65, 70, 75, 77, 80, 85, there we go, 90, 95, 105. What I'm saying is, when I average 10 people, Carl, when I average 10 people, I'm far more likely to score an 85 using that than scoring an 85 just picking one person at random. That's why the height of the mountain goes up, because when you're taking samples of 10 people, you're more than likely to average 85. If I take samples of 50 people, I'm really likely to. So if you imagine A is n equals 10, where I average 10 people at a time. If I start averaging 50 weights at a time, I'll be really likely to get an answer of 85. And for argument's sake, call that distribution C. And my standard deviation goes down because you're taking such a large population, you're more than likely to get a better representative of the full population, alright? So in general, if you can please remember this, when you take large groups of people and average them, standard deviation goes down, the amount of times you hit the mode increases. This results in a higher mountain, a higher, narrower mountain. Is that alright? Higher, narrower mountain. Okay, question 3. Samples of size 36. Now, note that 36 is bigger than 30. Why is that important? Central limit theory. Okay? I wonder if that even kicks in. Alright? From population of mean 12, standard deviation 2. The sampling distribution of the means are plotted on a curve. So you plot all your averages and you make a bell-shaped curve. Describe the shape of this curve, name the theorem you've adopted to support your description. Well, it's using the central limit theory, it's definitely going to be a normal distribution because my n value is bigger than 30. Is that okay with you guys? Okay. Explain why the theory you've mentioned can be applied when the shape of the underlying population is unknown. It doesn't matter if it's positively skewed. Doesn't matter if it's that's negatively skewed. Doesn't matter if it looks like your left foot, it's negatively skewed, and it looks like your right foot, it's positively skewed. Doesn't matter if it's positively skewed, negatively skewed, or uniform distribution. Basically, if you take over 30 of them, the means will always become normal. Okay? So I'll give you an example of this. If I had NBA basketball players, and what did we say about NBA basketball players again? What way would they be distributed? Usually very rare at the lower heights, really popular at about 6'6", 6'7", and then as you get to the bigger lads, they become really rare. So it looks a bit like your right foot, doesn't it? Alright? Now, when we average them, so if I take 10 NBA players at random, okay? So if I take 10, now one thing we got to learn about this, what did I tell you about positive, looks like your left foot, doesn't it? So did everybody agree that NBA players are negatively skewed? Yeah? It looks more like your left foot. Okay, I actually forgot to spell skewed, if I'm being honest. That's what stopped me. I think that's wrong. But anyways, negatively skewed. Now, here's what I recommend them. Right? What happens when you're negatively skewed? The mode is still top of the mountain. As in, a 6'7" NBA player is still the most common. What about the mean though? Smaller, it gets dragged downwards. The mean could be here at, let's say, 6'5", even 6'6", I don't really know, alright? And then the median will be in between the two of them, alright? But when I take for argument's sake, 30 NBA players at a time, and I average their heights. Do you get what I'm saying? I average their heights. What's going to happen? It's going to normalise the distribution, and the peak of the mountain will occur above the mean. Okay? But it will bell curve a negatively skewed graph for me. So I will still average, I'll average 606 more than any other score. 607 will be a rarer score. That's why it's further down this time around. It's dropped. It's no longer the mode. Okay? So that's what happens. You can take any distribution you want, provided you take over 30 people at a time, average it, and then it will become normally distributed when you distribute the means of your results. Okay? So an example would be I take 10 players and I get all 10 heights, and let's say for average sake I score 6'5" as a result. I go, no bother, 6'5", there's one dot. I do this hundreds of thousands of times, and eventually what will happen is 6'6" will be the most common, 6'5" will be the next, 6'7" will be there, and then then the rarer heights like 7 foot, they'll be increasingly rare, because you're not going to get 30 players that average 7 foot. That's why the standard deviation, in fact that should be narrower. Standard deviation really comes in narrow then. Is that okay? Now, oh God. Now, explain what the theorem you mentioned can be applied when the shape of the underlying population is known. I just said that. It has to be over 30 people you interview. Write down the mean and standard deviation of the sampling distribution. No bother. Otherwise known as the standard error. It's the same mean. The mean is unchanged. So what's the mean? The x 12. What's the standard deviation? Oh, sorry, the standard error? It's 2 divided by root 36, which is a third. Is that okay with you guys? Alright. Anybody want 4 done? You pair them off one at a time. So you do 4 and 6. You do 4a. You do 410. You do 6a. You do 610. And then you do 810. Does everybody get that? How many different combinations were possible? 6. What's the average of the initial one? 4 plus 6 plus 8 plus 10? What? So just give me a sec. It's 28. 28 divided by 4? 7. Now, what's the average of the distribution? That's 10. That's what? 12. That's 14. What's this? Oh, sorry. Oh, God. That's not the average. That's just what happens when you add them together. What's the average? Add them together, divide by 2. 5. Next one. 6. 7. Next one. 7. Next one. 8. Next one. 9. What happens when I add up all 6 combinations and divide by 6? What's the average going to be? Still 7. The parent distribution and the sampling distribution had the same mean. Okay, done. Show the mean of all possible sample size of 2 equals the mean of the population. I did that. Grand. Happy days. Right. Move on. Right. This one. Does it look more like your right foot or your left foot? Right foot. Most people are right-footed. Therefore, it's a positive distribution. It's a positive thing when you're using your right foot for most people. So, A is positively skewed. Describe the distribution B. Anybody? Normal. Explain why the central limit theorem can be used to describe distribution B, even though the underlying population is not normally distributed. We said this already. A is positively skewed, but if we take it in samples above 30, when we calculate means of thousands of samples, the sampling distribution of the means will be normally distributed because it's above 30, using the central limit theory. Okay. Let's keep going. Okay. I'll do 6 first. Alright. A random site. Alright, n equals 36. The population has a mean of 12 and a standard deviation of 3. Find a probability that the sample mean is greater than 13. Probability that a mean is bigger than 13. Now, I'm going to use set scores, but the problem with these set scores is, which one do I use? Should I use this set score formula here? Brian? Alright lads, do we use this set score?
No.
Why not? That is only for one score. It's not for 36 individual scores, so you cannot use that one. But you can use the one that's standard error. And what do I need to change x into then? X will need to change into x bar. Okay? Now, what score does it want us to get? A 13, doesn't it? So z equals 13 minus 12 all over the square root of what? 3 over root 36. Anybody get an answer for that?
2.
Is it 2? Okay, that's a set score of 2. Go to your tables. Go to a set score of 2. See the 0.97, 0.72%? 0.9772. So, if we bell curve this, okay, and what we're saying is that 0.9772 has a score below a set score of 2. So what has a set score, what percentage is above 2? What percentage is in the yellow region?
1 minus.
Yeah, 1 minus that. And what you get for that, Mick?
0.0228.
0.22?
8.
8. Okay, we cool with that? Alright. Who got that one? Mousy. Right. Now, this one here. Alright. Standard error. You go to page 54 or 34? 54? 34. You go to page 34, you look for the word standard error. And staring right at you will be sigma over root n. And you simply go standard deviation, no bother. Root n is 36, right? And that'll give me 0.3. Standard error is 0.3. Find the probability that the average time spent using a computer terminal is greater than 4.8. It wants me to get that a set score is greater than, an x bar score. Wait. Yeah. X bar is greater than, anybody? 4.8. You cool with that? Okay. Have to turn that into a set score. 4.8. So it's x bar, take away mu, over sigma over root n. What do we know about sigma over root n? It's 0.3. So it's 4.8, take away 4.2 divided by 0.3. Is that a set score of 2 again? And we get a set score of 2? Which makes it exactly the same answer as last time, doesn't it? So it's exactly the same score as I want everything above 2, which is 0.0228. Everybody cool with that? Shh. If you're in the great position that you're bored, I'll list a few questions for you to go after. We finished at 11, did we? And what's the last question of this exercise? Is it 16, is it?
Yeah.
16 is an excellent question. Do 13, 15 and 16 if you're bored, okay? I'm going to stay with question 9. Shh. Now, shh. Okay, so lads, what we do next is you want the probability that 4.1 is less than x is less than 4.5. I'm going to have to do 2 set scores to make this work. X minus mu all over the standard error, which we discussed as earlier, is 0.3. Okay, so 4.1 take away 4.2 divided by 0.3. Did anybody get a set score of minus a third or minus 0.333? So the set score will be minus 0.33. Okay. And then we're going to do the same thing for 4.5. And that will actually be a set score of 1. So probability that your set score of 0.33 is less than or equal to Z is less than or equal to 4.5. Okay. Not as smart as you guys. So I am going to have to draw myself a quick diagram to explain that to myself. Normally distributed. Set score of 0, dead center. Sorry, that's a set score of 1, isn't it? Alright, set score of 1 is 1 standard deviation above the mean. Set score of minus 0.33 is very close to the center. Okay, and I'm going to have to find out my answers for the two of them. Now, what we know is that this green region here, the probability of Z being smaller than minus 0.33 is the same, or smaller than equal, it doesn't really matter, it's the same as the probability of Z being bigger than 0.33. Bigger than 0.33 would be this sort of green region here. Okay, so it's going to be 1 take away the probability of Z being smaller than 0.33. So essentially, if I get a set score of 0.33, I can find out how many people are in this blue region, take it away from 100 or take it away from 1, and then I find the size of the green region there, which is what I was looking for. Okay. So, would somebody be so nice as to call me what a set score? Actually, I'll do. It's actually not better. Set score of 0.33. 0.3 is there, and 0.33 is 0.6293. Is that right with you guys? So this here is 0.6293. Take that away from 1 and what you get? Anybody?
0.3707.
This is 0.3707. Okay? So that's 0.3707. Okay. What's the next thing I could find? I gotta find the yellow area. Okay? And the yellow area, take away the green area, will leave you what you're looking for, which is the blue area. Yellow, the whole yellow area, which is the take away the green area, leaves you over the blue area. Now for the yellow area, we're going to do probability of Z smaller than 1. And if I know my stuff, is that 84? Not on the money though. 0.8413. Pretty close. So the whole thing is 0.8413, and you want your 0.8413, and you want to take away your 0.3707, and what you get?
0.47 is 6.
0.47?
Plus 6.
6?
Plus 6.
26.
Oh, 6.
Thank you. 4706. Alright, perfect. So you guys are currently having a crack at 13, 15 and 16. I'll just save this video.